I'm Norman Gilliland of Wisconsin Public Radio. Last year, in 2017, we celebrated the 100th anniversary of the first regularly scheduled broadcasts which took place in the physics building on the UW-Madison campus. This year, in honor of that, and to celebrate the 35th anniversary of the wonders of physics, Professor Sprott and his crew will be arranging a broadcast of their own, right here from the basement of the physics building. Let's find out what exciting and colorful things they have in store for us.
And now, from the basement of the physics building at the University of Wisconsin, we present the 35th anniversary show of the Wonders of Physics. Professor Sprott is just arriving on his 1921 Indian motorcycle. And now he's opening the door, and he's walking in the building.
Welcome to the Wonders of Physics. We're pleased to bring you this live radio broadcast using a replica of the original 9XM radio transmitter. We'll be presenting some of the best physics demonstrations from the past 35 years, as well as a few new ones. And our studio audience will be voting with their applause for their favorite physics demonstrations. And now, a word from our sponsor.
Hello, folks. Is your old doghouse too slow? Can't keep up with that pesky Red Baron? Well, now the sky's the limit in the 1917 Sopwith Camel. An agile, highly maneuverable biplane, the Sopwith Camel accounted for more aerial victories than any other Allied aircraft during World War I. And, unlike your doghouse, it can actually fly. Test drive the Sopwith Camel today.
Sopwith Camel is noted for its tendency to crash. Side effects include vicious spin characteristics, engine choking, and cutting out during takeoff, crashing on takeoff due to the full fuel tank affecting the center of gravity, tail heaviness in level flight, immediate uncontrolled spinning in a stall, and sudden right turns due to engine torque. Your results may vary.
Mr. Wykes, air travel has come a long way since 1917, and our first program today is Let's Fly with Captain R.O. Dynamic. Cheerio, everyone. Welcome to Let's Fly. My name is Captain R.O. Dynamic. 100 years ago, the state-of-the-art in motion was the airplane, or aeroplane as it was called back then. The most successful plane in World War I was the Sopwith Camel, introduced in 1917. In fact, Wisconsin's first flying ace, Rodney D. Williams, flew a Sopwith Camel. But what makes airplanes work? Well, we've all flown paper airplanes before. They look simple enough. But what holds them up? To answer that, we need to talk about the ocean that we all live under, our atmosphere. I need a really strong volunteer from the audience, from the studio audience here. You look pretty strong. Why don't you come up here? Hi, what is your name?
Cora.
Cora. Oh yeah, you've got a good grip there. Come here. Okay, Cora, pull those apart for me, please, will you? Anytime. Don't be shy. What's the matter? Oh, you know what? I forgot to tell you. There is something, there's a bit of a trick to this. We need to understand something. The ocean of air that we live under is heavy. See the end of my thumb? It's about 1 inch wide and 1 inch high. So every place I can cover with the end of my thumb, the air's pushing down with about the weight of a bowling ball. So you got a lot of bowling balls sitting on your head. So why don't you notice it? Well, here's why. You've got just as many pushing on this side as this side. So the forces are in balance. But what I did here, these are called Magdeburg plates, by the way. When I flip this handle, it pushes most of the air out from between the plates. So it's not so many bowling balls on the inside pushing out, but the same number on the outside pushing in. You would have had to pull with over 200 pounds of force to get these apart. You did a great job. Thank you so much for coming up here. So we've learned that a small imbalance in air pressure can generate a large force. I need a couple other volunteers from the studio audience. I need a parent and child. We'll start with you. What is your name, sir?
Isaac.
Isaac, come over here. And your name is?
Mike.
Mike. Pleasure to meet you. Isaac, come over here with me. You're going to sit on this like you'd sit on a horse, and that's the head. And Mike, you're going to stay right where you're at. So Isaac, right now, all the forces on you are in balance. We know this because you're not moving. So let's see if I can unbalance the forces a bit by pushing on the bottom. Well, you know what? I'm applying a force to the side of this board, but it's not going anywhere because there's another force opposing me. It's called the force of friction. There's a lot of friction between the bottom of that board and the floor. Now, there's a lot of things I could do to reduce friction. Me, I like getting rid of it altogether. Hey, Isaac, you're sitting on a hovercraft. There's an air blower there. When I turn it on, it's going to lift the board and you up a tiny little bit, but it'll reach a new balance point, but that new balance point will be off the floor. So by creating that imbalance of forces, we were able to get rid of all that friction, and you're able to move around. Great job, both of you. Thank you so much. So consider that what holds an airplane up is also due to an imbalance of forces. Oh, not from pumps or fans, but by the motion of the airplane through the air. Let's take a look at a cross-section of an airplane wing. Notice how it's curved on top, flat on the bottom. So as the airplane moves through the air going over the top of the wing has to travel farther, which means it has to travel faster to keep up. The Bernoulli Principle says that an increase in air speed causes a decrease in air pressure. Well, let's see what happens when we try that out. I need another volunteer from the studio audience. We'll have a few more volunteers, don't worry. What is your name?
Rachel.
Rachel. Rachel, I want you to hold this up here. You can kind of lean it on there. Just hold it there, and when I tell you to, I want you to let go of it. It's a little bit loud. Okay, let go. So, what was happening there? So Rachel, I was blowing air over the top of that. By Bernoulli's principle, it means that there was lower air pressure here, but there was higher air pressure under the ball, and that higher pressure lifted the ball up and sailed it out into the audience. Isn't that cool? Just like an airplane. Thank you so much. You did a great job. What do you think will happen if I blow air over the curved top of this roll of toilet paper? Let's find out.
Now let's vote with your applause for your favorite motion demonstration. Who liked the paper airplane? Who liked the Magdeburg Plates? Who liked the hovercraft? Who liked the Bernoulli ball demonstration? And who liked the toilet paper gun?
Well, that's all for me today. Next time on Let's Fly, we'll talk about Robert Goddard and his controversial idea about sending rockets to the moon.
And now, folks, a word from one of our commercial sponsors. Tired of high energy bills during this long, cold winter? Well, look to a new company for the answer, Solar Fusion Mining Company. No, we aren't talking about harnessing the sun's infrared radiation here on Earth. We're going to the sun and bringing part of it back. And with your investment, we can't fail. Sure, there are a few technical problems, but we will be going at night when the sun is not shining. So far, there has been a massive reaction to our IPO. Sue me. Invest now.
Past performance of Solar Fusion Minor Company stock does not guarantee future returns.
And now, to get our energy going at the atomic scale and to warm us up, we have that famous English physicist, Dr. Calvin Scale, who at times is an absolute zero.
Did he just call me a zero? Well, I'm going to take that as a compliment because I'm Calvin Scale. I'm super cool, and at times I'm okay. So let's talk a little bit about heat transfer, and the effects of heat and temperature on pressure and pressure on different materials. So let me start here by warming up a little water. I'm going to turn on this Bunsen burner, and I'm going to pour some water into this paper cup because a little later I'd like some English tea. So I'm going to put the paper cup on the burner and let it warm up, like so. All right. We're going to get those molecules vibrating back and forth and get that water warmed up. By the way, don't ever trust a molecule or an atom. They make up everything. Moving on. Oh, excuse me, I'm sorry. I don't have a handkerchief. Does anyone have a handkerchief anywhere? Thank you. Okay. Excuse. Was this a clean handkerchief? It isn't now. Okay, I'm sorry. Before I give it back, here, let me rinse it out for you a little bit here. Over here and see what we got. Okay, now it's wet. Sorry. So okay. So let me start it. See if I can dry it off for you a little bit. So okay, even though it's damp now. So. Oh my goodness. Oh no! Professor Sprott! Oh no! Oh! I'm sorry, I ruined your. Wait a minute. It's not even singed. What's going on here? What happened? Well, what happened is that this wasn't pure water. That's 50% water and 50% rubbing alcohol, very similar to what you might have in your medicine cabinet at home. And what lit on fire first was the alcohol because it has a lower kindling point or ignition point compared to the cotton in the cloth. But more importantly, there was water in here. And water is a great heat absorber. It has a very high specific heat, as physicists call, and that if something has a high specific heat, it can absorb a lot of heat into itself without rising much in temperature. And furthermore, if some of the water did get to the boiling point and started turning into steam, that takes a lot of energy too, called heat of vaporization. So the water, raising the temperature of the water and turning it into steam, absorbed the heat rather than into the handkerchief, and the handkerchief was saved. So thank you. Your name is? Cora. Cora? Thank you, Cora. Let's give Cora a hand. So let me get back to my cup here that I was boiling water with, okay? And I'm going to dump the water out of here, and you can see it's turned into steam. But if you look at the bottom of the cup, it's basically just a little singe on it. So I have a canister here that has some soaked paper towels with lighter fluid, charcoal lighter fluid. I'm going to start it on fire. And if you notice that flame goes up several inches, okay? And how does a flame work? Well, the hot flame then, they expand, those molecules in the flame expand, they take up a bigger volume, and we say it's less dense. Less dense materials rise up in colder air. So the flame goes up, cold air from the sides come in and take its place, and that air has oxygen and it feeds the flame. So we get a pattern like this. It's called a convection current. And convection currents are all over. A lot of your weather patterns are due to convection currents. So now what I'm going to do is I'm going to take this cylinder this screen cylinder and put it over the top of the flame. And this cylinder is on a rotating disc, and I'm going to rotate the disc and watch what happens. Okay, this is called a fire tornado, and fire tornadoes actually do exist in real life. If you have out west in the wildfires, if you have strong swirling winds, you can get fire tornadoes that go up several hundred feet. Now let's talk about the effects of pressure. Remember Captain Dynamic earlier talked about pressure and this sea of air we have above us, and the effects of that pressure on your boiling point and freezing point of water. Does anyone know the boiling point of water? Anybody? 212 degrees or 100 degrees Celsius. By the way, in my scale, it's 373 degrees in the Kelvin scale. But that's only if you're at 1 atmosphere of pressure. So that's the boiling point in New York City or in San Francisco. Here in Madison, Wisconsin, we're about 700 feet above sea level. The boiling point is a little bit less, as you can see. And it's even less in Denver, Colorado, and at the top of Mount Everest, it's even lower. So what I have over here is a flask that has just distilled water in it. No trickery in this, just plain distilled water. It is exposed to atmospheric pressure right now. So the boiling point's around 100 degrees Celsius or 212 Fahrenheit. I'm going to lower the pressure over the top of that flask. I'm not going to do it by raising up in altitude. I'm going to flick a switch on a vacuum pump, which is going to suck the air out, and watch what happens. It'll take just a few seconds, but it starts vigorously boiling. I lowered the pressure to the point where room temperature was warm enough to boil it away. Now, if I let this go, this is turning very cold. I can feel it being very cold. And if I let that go a few more seconds, you will start seeing an icy skim on the top. Why is that? Well, remember I said to boil something, to go from liquid to gas, you need heat of vaporization? There's no outside heat here. So it took the heat internally from the water and from the flask to do that. So wow, you can boil and freeze water at 32 degrees at the same temperature if you lower the pressure. So I'm going to take a match here, put it on the end of this stick, and come over here. Light the match, and we'll see what we get. What do you think? Helium. Yeah, it blew up, but it would have been no different if I'd taken a pin and kind of just popped it up there, okay? So it was pretty obvious it was helium. Now, one of the things in physics is you should never take anything for granted. And another principle in physics is that you should always repeat your experiment to see if you get the same results or different results. So we're going to blow this one up then. We'll put my match on here.
I'm out of here. You're on your own.
He is such a chicken. Okay. All right, you may want to cover your ears on this one. Pretty obvious we had hydrogen in there. Hydrogen, very explosive gas, a lot of energy, very light gas. That's why it's used in spaceships and rockets to get outside of our atmosphere.
And now let's vote with your applause for your favorite heat demonstration. Who liked the boiling in the paper cup? Who liked the non-burning handkerchief? Who liked the fire tornado? Who liked the freezing by evaporation? And who liked the exploding balloons?
Thank you.
And now, folks, another word from a commercial sponsor. Do you want to take your music wherever you go? Well, now with the Pauly portable player you can. Weighing in at only 30 pounds, our record player lets you be the life of any party. Pauly, a proud sponsor of Sound Off with Riley Rayleigh.
And now, to break up the talk radio with some sound waves of her own, it's Sound Off with Riley Rayleigh.
Well, hello everyone. I'm Riley Rayleigh, and this is Sound Off. Today we're going to be bringing you some of the top songs of the last 50 years and some science along with them. Now, since we're on the radio, it makes sense to talk about sound, right? Well, sound travels through the air or other things as a wave. Basically, the air molecules are squished together and pulled apart, like you and our studio audience can see in this diagram. When those squished and pulled apart bits of air hit our eardrums, our nerves in our brains take that mechanical pressure, you know, the squishing and pulling, and make it so that we hear a sound, or a song like this one from the 1950s by The King.
You ain't nothing but a hound dog, you're crying all the time.
Now, the speed at which sound travels is going to depend on the thing that it's traveling through. Sounds will travel faster through lighter gases, like we just learned, like helium. So,
a molecule of helium weighs about 7 times less than your average air molecule, meaning the sound of my voice travels about 3 times faster. And in this case, faster means higher pitched.
kind of makes me sound like all the fangirls who saw our next group, the Beatles. Now, sounds travel fast through lighter things, right? So it makes sense that they're going to travel slower through heavier things. There are also gases that are heavier than air, like sulfur hexafluoride.
A molecule of sulfur hexafluoride weighs about 5 times more than your average air molecule, so the sound of my voice travels about 3 times slower and sounds much deeper.
It's kind of the opposite of our next group, the Bee Gees. Now, there are some ways to see what a sound wave looks like. You know, to see those squished and pulled apart bits of air. The most sciencey way is using an oscilloscope. However, it's just not really exciting. You guys know what is exciting? Fire. Lighting things on fire, yeah. So, since sound travels by squishing and pulling apart bits of air, the pressure and density will change at different points on this tube if I send a sound wave into it. And when the pressure and density changes, you'll see that the fire changes too. So let's turn on our sound. Can you guys hear that? So you can see the different parts of the wave. So let's see if we find another frequency here. We can get different looking waves because of the different sounds. So you can physically see what the sound waves look like. And speaking of physical, this is Olivia Newton-John. Every time that somebody plays an instrument, you know, a guitar, violin, flute, trumpet, anything, they're going to be creating something called a standing wave. Now, the idea behind this is that sounds like to travel in the way that's easiest for them. So they're going to create a pattern that kind of looks like that it can just keep going and going and going. Now, I have something here that will create a standing wave. It's not really an instrument, but of course it involves fire. So let's light this flame. Now, since sound travels, once again, by squishing and pulling apart bits of air, the density changes, right? And another thing that we learned that can change the density of air is heating it up, like we can do with this flame. And what happens to less dense air? It rises, right? So if I were to put this tube over the flame, it's kind of like blowing air through a really big straw, and it'll create a standing wave that sounds something like this. Yeah, so I also have a longer tube here. Do you guys think that this long tube will sound higher or lower pitched than the short one? Higher or lower? Why don't we find out? Okay, ready? 3, 2, 1. So it was lower. So my longer tube had a longer standing wavelength, which meant it sounded deeper. Shorter tube, shorter wavelength, higher pitched sound. Now, those sounds were kind of obnoxious though, weren't they? Yeah, speaking of obnoxious, here's the Macarena. So since sound travels as a wave, it has some power to it, like water waves or things like that. Also turns out that strings and tubes aren't the only things that can have standing waves and resonant frequencies. Everyday objects, like say this glass, can also have resonant frequencies. However, some things really don't like having standing waves in them. For example, I have a sound wave here that we have perfectly tuned to the resonant frequency of our glass. And you can see as we turn up the power, our glass will start to shake because of all that power from the sound wave. What do you guys think would happen if I turn up the sound even more? It'll break. Help me count down. Ready? 3, 2, 1.
And now let's vote with your applause for your favorite sound demonstration. Who liked breathing helium and sulfur hexafluoride? Who liked the flame pipe? Who liked the hoot tubes? And who liked breaking the beaker with sound? And now, to get some sparks out of your radio, we have our own electrifying duo of electrifying hijinks, Sparky and his sidekick, Mr. E.
Whoa there, partner. Yep, it's time for another hair-raising adventure of Sparky, the Wonder Eel. He's electric. And me? I'm a real mystery. That is short for Mr. Electricity. Your low-resistance conductor of today's episode. But first, a word from our sponsor, Faraday Cages, shielding you from all of life's unwanted E-fields.
Yes, listeners, it's true. Electric fields are nearly everywhere. Cell phones, microwaves, power outlets. It can affect your potential, and not always in a positive way. Well, the kind folks at Faraday's have the perfect refuge. Just reserve a vacation in one of Faraday's equipotential cages, and you can be field-free for as long as it takes to get your charge balance back. Soothing, peaceful, relaxing, and highly recommended by all of Sparky's closest neighbors. Now back to the show.
Sparky hopes everyone knows that there are two kinds of electrical charges, positive and negative, and objects with opposite electrical charges attract one another, but things with like or the same electrical charge repel. There is a simple but classic demonstration to show this. All it takes is two identical black plastic rods, some of Sparky's fur, I guess he's a mammal, and some vigorous rubbing. But first, I have to convince you that these rods right now are electrically neutral, so there are no long-range electrical forces. And so I'll put one of these rods on the hanger like this, and I'll bring the other one, and you'll see that there's no real force until they actually touch. But now, I'll take it back here. Oh, gesundheit, Sparky. Now, we've transferred electrical charges, and since these rods are identical, they should have the same charge, and so there should be a repulsive force. And let's just see. I can't even get close, see? Oh, I didn't forget. Sparky also hopes everyone knows that electricity or electrical currents or charges can flow through conductive objects similar to water flowing through a pipe, except the electrical charges, usually electrons, they flow right through the metal itself rather than in the pipe. In fact, if we give those electrons enough electric potential, they'll even flow through the air. This device, a Jacob's ladder, does just that. Watch what happens when I turn on the switch. Do you see that? So what's happening? Well, if you look underneath, there is a blue box, and that's called a step-up transformer. And that raises the electrical potential to thousands of volts. And where the two metal electrodes come close together, the electrons go through the air and complete a circuit. But you don't really see the electrons. What happens is those energetic electrons excite the atoms inside the air molecules, and excited atoms emit characteristic colors of light that you can see. Poor Sparky, he's just green with envy. Well, that marching motion of electrons in charge per second is called a current. And speaking of currents, did you know Sparky's favorite subject in school? Current events. You know, he really is well grounded. I just couldn't resist. So electrical currents can also cause objects to move. A device which converts electrical energy into mechanical energy is simply called an electric motor. In 1822, a scientist, Michael Faraday, invented the first electric motor. But what Sparky and I really like about this motor is you can make this electric motor at home. All it takes is a AA battery, which we've taped up so you can see, some super strong conductive magnets on either side. You see them here, 1, 2, and then just a long coil of bare wire. And all we have to do is insert the assembly into the coil, completing the circuit, and now for this demonstration, I will need an energetic volunteer from the audience.
Mr. E, I just noticed that we have with us today a very special guest, and I think we should use him in this demonstration.
That sounds like a plan.
Ladies and gentlemen, please give a welcome to Norman Gilliland from Wisconsin Public Radio. Now, Norman, I know you used to come to these shows years ago. Is that correct?
Yeah, when I could get in.
Oh, it's been popular for many years.
Yes.
And how long have you worked for Wisconsin Public Radio?
34 years.
30, just exactly as long as we've been doing these shows. Now, 34 years, that's not very long in the life of Wisconsin Public Radio.
Yeah, it's only about a third of it.
Right. Did you know that this very apparatus that we're about to show you was one of the first radio transmitters used by WHA?
I've heard rumors.
Well, here it is, and we're going to give you a close-up look at it.
Okay, so this is Norman and Sparky's new electrical adventure. Is your insurance all paid for?
No, but I noticed that Clint was awfully good with that fire extinguisher, and I wonder if that's a lot of practice, or what are we up to?
We'll find out. Well, come with me, and we'll take you over to our Faraday cage. Everyone take notice. It looks a little like a lot like a electric chair. Make yourself at home. All the conveniences. Are you comfortable?
Oh, yes.
All right, we'll just latch you in here. Now, the cage is metal, so all of the electrical sparks and electricity will go through the cage rather than through Norman, which is a good thing. I'll just run the control panel. You may not want to touch the wires. Even if you do, it's probably okay. You ready? Ready. All right. I'll engage the spark gap, the solenoid, and turn up the potential. How are you feeling?
Still here.
That's good. Glad to hear it. And Sparky looks pretty good too. Let's give Norman a great hand. Well, so far we've talked mainly about electrical circuits. In fact, electric fields can move through space if they're joined with a magnetic field. In fact, one of the devices that does that has electric fields that's in your house is called a microwave. Did you see Sparky's tail move? You probably didn't. That's what Sparky calls a microwave. In this case, it's hard to see those electric fields, but we can do an experiment to show that they are there. We're going to do something you're not supposed to do at home, and never, ever do this, is put fine metal wire inside the microwave because electric fields condense or become very strong at fine metal wires. So inside this ordinary old-fashioned light bulb is a filament that goes round and round, and rather than sticking in a light socket, in the name of science, we're going to do this experiment and see what happens when the electric field collects at the filament. Are you ready? Let's go. Look carefully. You'll see. So it's similar to the Jacob's ladder in that it produces all sorts of characteristic colors of light due to the excited atoms near the filament. Well, Sparky is getting all charged up in our electrical adventure. Another thing that can get charged up is inside this mysterious box over here that's orange. It's called a capacitor, and a capacitor is a very simple device. It's just alternating metal plates. But when I push this button here on this little box, we're going to use this high voltage battery and charge those plates positive, negative, and positive and negative. Now, those charges want to attract one another, but they're not allowed to sort of collect together or form a current until I release the button. We will take all of that charge we're storing and pass it right through that aluminum foil in a fraction of a second when it hits about 5,000 volts or 50 on the galvanometer. Is it there? It's a little hard for me to see. Tell me, are we up over 50? Yep. All right, this could be a bit loud. Let's go. Well, we finally managed to get rid of that stationary electrical charge we've been storing. Everybody should be positively ecstatic.
And now let's vote for your favorite electricity demonstration. Who liked the electric forces on the plastic rods? Who liked the Jacob's ladder? Who liked the Faraday train? And who liked the Tesla coil and Faraday cage? Who liked the light bulb in the microwave oven? And who liked the exploding foil?
Well, until next time, radio fans, hi-ho silver away!
Our next radio program will be a reading of Sherlock Holmes by his assistant, Dr. Watts On.
Good afternoon, everybody. Welcome back to another exciting reading of Sherlock Holmes' Magnetic Mysteries with me, Dr. Watson. Will Sherlock Holmes solve the mystery, or has he met his polar opposite? Find out today on Sherlock Holmes, A Brilliant Induction. But first, a word from our sponsors.
Hey, amateur detectives! Ever go looking for clues only to have your batteries run out? No way to turn that flashlight on? Power up the camera or call for help? Well, try Faraday's new ultra-high capacity capacitor. Guaranteed to store more charge than those pesky batteries.
It was a dreary London morning. Sherlock Holmes and I were having our morning tea. I was reading the newspaper and noticed a crime had been committed in the London Underground. A thief, after stealing wallets and purses, jumped in front of a subway train, vanishing mysteriously.
Why, Watson, people do not just vanish mysteriously. The game is afoot.
Sherlock and I wandered down to the subway station and began looking for clues. I went over to the subway tracks and took a look and said, Sherlock, there is no way a person could survive if they jumped in front of a train.
Quite to the contrary, Watson. One only needs to be propelled upwards very quickly to get out of the way of a moving train. Look here, Watson, an electromagnet and the railway's electrified center rail. The thief must have used this to vault over the train.
Now, listeners, at the time I didn't know what an electromagnet was, and I'm sure some of you are interested to learn yourselves. So I will explain as Sherlock explained to me that day. An electromagnet is simply a hunk of iron surrounded by a copper coil. When that copper coil has a current pass through it, if we do this very quickly, we'll produce a magnetic field. This magnetic field can then be used to induce a current in any metal object. I have here a ring of aluminum, such as the thief may have had on his shoes, and that current in the ring will feel a magnetic force. Let us find out. 3, 2, 1. Sherlock, that ring didn't jump nearly high enough to get over a train.
A great observation, Watson. But there are things we can do to make the ring jump higher. Say the thief had a bottle of liquid nitrogen on him. If we cool that ring down with that really cold liquid nitrogen, we can change the electrical properties of the metal. It becomes less resistive, allowing a larger induced current to flow on the ring, which in turn allows for a larger magnetic force to exist on the ring. Show the nice audience, would you, Watson?
So, liquid nitrogen is at a very warm temperature of negative 321 degrees Fahrenheit. Not something that you'd want to be handling just out of the blue. So now, with liquid nitrogen, let's see how much higher we get. 3, 2, 1. So, we doubled the height of the ring jump there, but that's still not quite enough to get over a train. Let's say, on the other hand, the thief, in addition to that metal ring on his boot, happened to have a stilt of iron or something. Now, you're probably wondering why a thief would have a stilt of iron on his boot. Well, with an electromagnet, the magnetic field tends to taper off right where the iron ends. So by adding an additional piece of iron, we'll be able to extend the magnetic field up and put the ring in that magnetic field longer. Longer time in the magnetic field means hopefully we'll get it to accelerate faster. So now the question is, who thinks this setup will get someone to jump over a train? Let's find out then. 3, 2, 1. Okay, Sherlock, I'm with you now. The thief, he could use the electromagnet, jump up onto the train. But once he gets there, how's he stay on? A London subway sure does move fast.
Elementary, Watson. If the thief already had metal rings on his shoes, and if he had pre-planned the robbery, as one would do if they were about to jump in front of a train, he must have had some way to stay on or above the train. He likely levitated himself.
Now, listeners, levitation, that might sound like madness, but Sherlock Holmes, he's a brilliant detective. And later that day, we happened to find a set of train cars with a pair of magnets on their roof. Now, how does one use a pair of magnets to levitate themselves? Let's find out. So this setup is similar to the ring launcher, except instead of running a single pulse of current through the ring to project something upwards, we will rapidly alternate the current between positive and negative in the electromagnets. Similarly, instead of an aluminum ring, we have an aluminum cylinder. In the cylinder, we'll induce a current from the changing magnetic fields. That current will feel a magnetic force from these two and levitate. Let's find out.
Watson, the magnets need to be turned on.
Right you are, Sherlock. This time, let's see what happens now with more power. So you see here, I'm spinning the cylinder in between there. The magnets force it to the center. The blue one's lifting it up, the orange one is pushing it down. I can spin it side to side, push it up and down a little bit, and as long as it stays somewhere relatively close to the center, the magnetic forces keep it held in place. And when we turn off the electricity, right back to the earth we fall.
Okay, Watson, back to the story.
Right. Sherlock Holmes and I continued to look for clues down a subway tunnel. We wandered along until we found a service store where the lock had been cut. But the lock was not just cut, it was melted right to slag.
As you might well have guessed, the thief used magnets to melt the lock.
Now, with the levitator, we were using energy, magnetic energy, to hold that up. If instead your thief with your pocket electromagnet hooked up a pair of wires to this stainless steel rod representing a lock, we can see that instead of using the energy to levitate something, we can use that energy to heat up the stainless steel rod.
If you heat metal up enough, it will melt.
Now, Sherlock, the real question is, what kind of thief has the kind of knowledge to commit this crime?
Only the vile Professor Magnuson could possibly do this, using physics to rob people.
Professor Magnuson, didn't you catch him last week? Wasn't he scheduled for execution?
He was. He must have faked his death in the guillotine last week. Here, let's see how that's possible. We just happen to have a guillotine right here.
The guillotine is a rather simple device, medieval one might say. It works by lifting up a heavy metal blade and letting gravity do the work. The question then becomes, how does one with a knowledge of magnets use that knowledge to save oneself from such a grisly fate? Well, let's say that Professor Magnuson, instead of letting the guillotine just fall, had placed a set of magnets at the base. Let's see what happens then when the blade falls this time.
And now let's vote with your applause for your favorite magnetism demonstration. Who liked the ring launcher? Who liked the levitated ball? Who liked the induction heater? And who liked the magnetic guillotine?
And now, folks, a word from a commercial sponsor. Hi, folks, is that gravitational force getting you down? Well, then, make a motion over to Newton's for some of the best rings in the universe. Don't confuse them with someone else's dark and tasteless corpuscular theories. These rings are light as can be. Remember it well, listeners. Newton's rings run circles around the competition.
Hi, Professor Sprott. I'm in early a few minutes before my show. Can I tell you about my new passion for painting? Too bad I can't share it over the airwaves.
Well, actually, we're already on the air. And now it's Late Night Lights with Dr. Sunshine Maxwell. For those of you who are still awake, she'll help you see in the dark.
Well, hello, my late night nightlights. We've got a lot about light to learn tonight. First, can I get an energetic volunteer to come and help me? Right here on the end in gray, can you come on down? So light is vibrating patterns of electricity and magnetism. And there are different wavelengths that correspond to different energies. And what is your name? Tegan. Hi, Tegan. You're going to help me demonstrate how energy and wavelengths are related. First, we're going to demonstrate short wavelengths. Can you jump up and down really fast? Excellent. Now, we're going to look at the other end of the spectrum and demonstrate long wavelengths. Can you jump just as high, but take a lot of time in between? Excellent. Now, which of those took more energy? The first one. Did it tire you out? Yep, that's why I had you do it instead of me. Can I get a round of applause for my volunteers? So just as we saw, the short wavelengths have more energy than the longer wavelengths. And only some of these wavelengths are the visible light, but in visible light, that means that blue light has more energy and red light has less. Now, just to the more energy side and shorter wavelengths than blue light is ultraviolet light, or UV. And on the other side of red light is the infrared, or IR, that has even less energy than red. And today we're going to see all of these different wavelengths in practice. So even the white light that we see from lights in the room like this, or the sun outside, can be broken up into the different wavelength colors. And we can do that by sending it through a prism. So we get a nice rainbow effect. Now I'm going to turn off this black light and bring down this fluorescent screen, and we're going to see if we can get it to light up if we use a laser with enough energy. So first, do you think my red light will get it to light up? No. Nope, it didn't. What about my green one? No. What about my purple one? Yeah. Maybe I shouldn't quit my day job, though. Now, transparent materials don't absorb visible light. That's why we can see through them. And we've got an example of that with this laser here. So I've got a blue laser, and I've got smoke in a can that I can put in here so you can actually see the laser beam. And you'll be able to see it in the tube here. But it's harder to see in the glass here because this is laser protective glass. It'll also mean that the colors of anything I put in there will look a little different. And I'm going to put this purple colored balloon inside. And that balloon can absorb the laser light and then pop. So let's see what happens when I turn on the laser. Well, now I can use that to change the color of this red balloon. Let's put it in and see what happens. I'll turn on the laser. And what started as a red balloon now looks like an orange balloon. Let's put it in one more time, though, and see what else can happen. And what we've got left is a clear balloon. It didn't absorb the laser light, and so it stayed whole. Now I'm going to need 2 more volunteers. Hello. So we're going to come down, and you guys can hide behind this piece of plastic here. And we can't see them in the visible light because the plastic blocks it. But in the infrared, we can see through that plastic with no problem. Can you guys wave to us? Excellent. You can look up and see what you look like also. Fantastic. Now stick around while my colleagues change the screen for a second. Now one of the other things I can do with my IR camera is check myself out in the mirror. And to make a mirror, all I need is this dull piece of stainless steel. All the scratches that mean it's not a very good visible mirror don't affect the longer wavelengths in infrared. And so, I look pretty good. Okay, now I'm going to give my volunteers 2 squirt bottles of water, 1 warm and 1 cold, and now they get to be the artists. So you guys can each take half of this screen and draw whatever you'd like on it. The bigger, the better. Remember, if you want to write something, we see it backwards, so it might just be easier to draw something. Oh, and they've already started. So in bright yellow, you'll see the warm water, and in the dark purple, you see the cold. And you'll also notice in the warm water, as it evaporates, what's left behind is cooler, and so it switches from bright yellow to dark purple. Fantastic. Thank you to my wonderful volunteers. You guys can leave the water back there and come take a bow. Well, looks like the sun is coming up, and that's all for our late night lights. Join us next time for another light adventure.
And now let's vote with your applause for your favorite light demonstration. Who liked the fluorescence demonstrations? Who liked popping the balloon with a laser? And who liked the infrared camera? And now, Peter, which demonstration got the most applause for the entire show?
Well, listeners, I've been judging closely and monitoring the applause meter, and the winner is the paper toilet gun. Toilet paper gun. It's wiped out the competition.
Oh. Now, some of you may be thinking we're just pretending to broadcast this. But in fact, if you happen to have a portable radio, as I do here, if you take it and tune it to 550 kilohertz down at the bottom of the AM band, you should be able to hear us broadcasting. And to prove that, I'm going to turn off my wireless microphone and take this old-fashioned microphone from 100 years ago
and show you that we are indeed broadcasting. This is 9XM broadcasting from the basement of the physics building at the University of Wisconsin, just as was done for the first time 100 years ago.
Now, when I started doing these shows 35 years ago, I had no idea I'd be doing it 35 years later. But our audiences have been extraordinary, and we thank you for listening over the years. But we need your help in order to continue the programs for many years to come. Please go to wonders.physics.wisc.edu, click on Donate for your tax-deductible contributions. And now I'd like to end the show the way we have ended every one of the shows over the past 35 years, by making for you a cloud. For this, we use 25 liters of liquid nitrogen, this very cold stuff, and we force nitrogen gas into the container. That forces the liquid up into this pipe on the top. This pipe has several dozen small holes. The liquid nitrogen will come out very, very cold, come in contact with the air, and the water vapor in the air will condense into tiny droplets of liquid water. And that's what we call a cloud. And so with that, I will put on my hat and thank you all for coming.